can get to you, right? And I'd like to walk around. So we've talked about neural networks all semester long, and we've focused on how we can do things like classification and prediction and time series analysis and modeling language and things like that, right? We're going to start with a new problem. So, and that is how to learn to generate stuff, right? We've already done this for language, but that was a kind of abstract concept. Language is something we might understand, but what about images? You have given a large collection of images, of faces, for instance. And from this collection of images, can you try to learn a model that can generate, that can draw new faces? Guys, shut your laptops, please. Yeah. You mind? Yeah. OK, thank you, right? So what does it mean to be able to draw a new face? To be able to draw a new face, essentially what you're saying is that I want to learn the distribution of face images and somehow, and I want to be able to draw samples from this distribution. The question is, what is this distribution? Obviously, it's not something nice and tidy like a Gaussian. It's probably something very ugly. How do you characterize it? And even if you manage to characterize this really hideous distribution, how do you come up with a mechanism for drawing a sample from this distribution? Or a collection of landscapes, right? Again, if I want to see a whole bunch of landscape pictures and then figure out how to draw new landscape pictures, how can I learn to do this? How do I learn the distribution of landscapes? And then how do I learn to sample from it? Now, in all of this, there's something that we sort of pin our principles on. And that is that anytime you have data of a very specific kind, it means it doesn't belong to any other kind, right? A picture of a face is not a landscape. A picture of a face is not white noise. It's not a spacecraft. So we're actually eliminating possibilities. When you eliminate possibilities, what is it you do? So the space of all possibilities is everything. When you eliminate when you impose some restrictions, when you eliminate degrees of freedom, you sort of keep restricting the possibilities. Every time you restrict the possibilities, you're saying that portion of the space, that's not faces. That's not possible, right? The only thing that occupies all space, what would it be? Anyone? Take a guess, guys.
It's like noise.
It's just noise, right? If it's unstructured, it's noise. If it's structured, it's not. There are some things it simply cannot do. By the time you get to something to be sufficiently structured, what you will find is that all the data of this particular category lie in a very small region of the overall space. Typically, the volume of the space that they lie in is going to be so small that it's close to zero, right? And so the idea here is that there is some underlying manifold, some curved surface, which represents the structure for this data, and all data from that class lie on or close to that surface. Anytime you want to draw something that belongs to that class, you're going to have to pick something from that surface. But then how do you characterize this surface? How do you characterize this manifold? And how do you draw from it? So we've already seen one way of characterizing manifolds. If you were there in the last class, we learned about autoencoders. And what did we say the decoder in an autoencoder did? Anybody remember what did it do? Anyone? So it's there on the slide, so you can help me, right? What did we say the decoder of an autoencoder did? Someone? Anybody on Zoom? Do you want to answer this?
Linear classification.
So what we said, OK, if our autoencoder had linear activations, what did it do? We discussed this in class. Hopefully, you were paying attention. What does an autoencoder with only linear activations do? Do you remember that? So maybe someone on Zoom is answering. Can you check? It performs principal component analysis. You remember that, right? And so what happens if I modify the linear activations and can make them non-linear? What was it doing? Someone on Zoom is answering, I'm sure. It performs principal manifold analysis. It actually finds the principal manifold that the data lie on, and then represents everything as being on this manifold. So we already have a mechanism for capturing the underlying manifold. We saw this, and that's what we used in my little toy examples, where I learned an autoencoder from, say, the examples of saxophone music. And then when I took the decoder and just excited it using any odd excitation, it produced outputs that sounded somewhat like a saxophone, right? Or if I want to now use the same mechanism for drawing pictures of faces, I could train an autoencoder and lots of face images. And then I can use the decoder. If I do it right, the decoder is going to learn the manifold of all faces, the small section of the space on which faces lie. And then when I excite the decoder, it's going to generate something lying on the face manifold. And this is what we are going to be able to use. But then we have a problem. And the problem we saw in the last class, so we can just use the decoder to generate more faces. The problem was this, that when I trained an autoencoder, I did not have any constraint on what the hidden latent variable could be. So the way our autoencoder was trained, you had an encoder, your data went in, you had a z, this was the latent variable, that was what the variable that connected the encoder to the decoder, and then this variable went into the decoder to generate data all over again. But we didn't say anything about what the z could be, right? And if we train this properly, we know that this decoder is only able to generate data on the manifold that the data lie on. So in our example, over here, the data all lay on a spiral. So if my hidden latent variable is unidimensional, just a scalar, that means that the decoder is going to basically fold a one-dimensional space. What is a one-dimensional space? It's a line, right? And it's going to fold this line to match the data as much as possible. It's going to learn the spiral, which is indeed what it does. But what this entire structure is missing is a restriction on z. So if these were my z's, if this is my z-axis, I pass all of my training data through my autoencoder. Since we have no restriction on what the z's can or must be, you might find that for part of the data, it's using z's in this range. For some other part of the data, it's using z's in this range. And then all the rest of it goes for the rest of the z's. Now, it's only on these z's that you're going to get the spiral. For z's that were not seen or very rare in the training data, you have no idea what it's going to, it's still going to be a one-dimensional curve. You have no idea what that curve is going to be, right? Which is why you have this strange situation over here. Most of it goes around the spiral, but then here and out here, those are z's that were not seen in the training data. If I want to use this mechanism to generate images of faces, would this work in this naive manner? If I just trained an autoencoder and then began feeding random z's, am I likely to get faces? What do you think? Can you speak up?
No.
No, why not?
It's not enough to carry the information for the face.
It doesn't tell you what z's are going to produce valid faces, right? Even in that low dimensional space, the volume of z that actually will generate a face is going to be very small. More often than not, if I randomly choose a z from it, what's going to come out is going to be any odd thing. So we need a way of constraining the z's so that we know exactly what z's to feed for the model to generate faces. Is that making sense to everybody, right? Okay. Guys, since this is my first in-person class, I'm going to ask you to yell out yes every time you understand what I say. And I will not continue till I hear a really loud chorus, because that's the only way I make sure that you guys are awake. Even if you fall asleep, everybody else's yeses will wake you up. Okay. Now, here's your first poll. falling behind. It's
Second research part.
The 746.
And second.
I follow another strange rule in class. The first person to shut their laptop tells me that the poll is answered. They are timing it. So Lindy over there thinks she's answered the poll, right? Okay, guys, we're out of time, right? Shut your laptops. Can anybody answer the question? First one, true or false? Someone on Zoom, true or false? Is anyone replying? No? Guys, what happened? True, okay. Do you agree that this is true? Yes. Okay, can everybody say true together? 1, 2, 3? True. Thank you, right? What about the second question? Which are the true statements? What's the true dimensionality of the manifold? Anyone?
The second one?
Second one is no greater than the dimensionality of the latent variable. So here's what happens, right? If I multiply a two-dimensional vector by a 4x2 matrix, the result is in four-dimensional space. But all the data are still going to lie in a two-dimensional plane on the four-dimensional space. You know this from linear algebra, right? This is not special. There's nothing special about linear transforms. Even if it's a nonlinear transform, all a nonlinear transform does is to fold this sheet. So if I take an n-dimensional space and then put it through some kind of a transform, it gives me an m-dimensional output where m is greater than n. The result is still going to lie on an n-dimensional surface, which could be planar or curved in the m-dimensional space. And so that's why we're able to use the structure, right? It's going to be a manifold, but the dimensionality of the manifold is the same as that of Z. Okay, and this is what we're actually using. And so now, we've decided I'm going to assign some dimensionality to Z. This is my hypothesis that the data lies close to some Z-dimensional surface in the larger space, right? Images are million dimensional. If you have 1 million pixels, if you have 10 million pixels, they're 10 million dimensional. But the actual images of faces are going to be maybe on some 3 or 4 or 100 dimensional surface in this million dimensional space, which means Z has to have 100 dimensions, right? So, except we have no restriction on what Z could be. It's a huge space. How do I impose a restriction on Z? I can do this externally. And the way I can do it is say, my Z has to follow a standard Gaussian distribution. This is my way of imposing a restriction because the model allows you to do so. So Z is drawn from standard Gaussian, right? And now if I train the model properly, I can draw samples from the standard Gaussian and pass it through the decoder, and it's going to generate faces. So how exactly do we do this? Is this making sense?
Yes.
Right, yeah, thank you, right? So how exactly does one train the autoencoder to do this? That is where things get hideous. We are done with the easy portion of the lecture. The rest of the lecture, you're going to have to pour coffee into your eyes to stay awake. Please do so, okay? So how does one train an autoencoder to ensure that the hidden representation has a specific distribution, such as standard Gaussian? There's nothing magical about standard Gaussians. You could use any odd representation for the distribution of the latent variable. Why do you think we use Gaussians? Anybody? Any idea why we would use a Gaussian as opposed to something else? You look like you know the answer.
I don't know the answer.
Okay, well, there was a look of knowledge on your face. So anybody?
It's a little easier mathematically.
It's easier mathematically. That's not it. The Gaussian is the most unstructured distribution data you can think of.
Because if you have a bunch of samples, they all converge to normal.
And that's, okay, that's a consequence, right?
Yeah.
So Gaussian, of all possible distributions, the Gaussian is the one with the highest entropy for a given variance. It's the most unstructured data. And that's why when I keep adding more and more noisy data, the structure keeps decreasing, and then it's going to become Gaussian, because that's the most unstructured you can be. So if I don't want to make assumptions about my latent distribution, having a Gaussian distribution for it makes the most sense. That's why we start off with a Gaussian, right? If you know something about it, then you could use the other distribution, right? So here's what a standard Gaussian looks like. It's, you know what a Gaussian is. It's this nice bell-shaped. If I have an n-dimensional Gaussian, it's going to be an n-dimensional bell curve. It's going to be a bell curve along every dimension. All the dimensions are independent of one another. So the joint distribution of Z1 and Z2 is going to be the probabilities of the product of the probabilities of Z1 and Z2. They're all independent. And each component by itself is isotropic, meaning it has zero mean and unit variance. So the probability, the formula for it is 1 over square root of 2 pi raised to d. D is the dimensionality of the variable. And this is the nice bit. That's e raised to minus 0.5 norm of z squared. So what this really means is that the logarithm of the Gaussian falls off as a quadratic. So the Gaussian basically follows the exponent of a quadratic. And now we know something about quadratics. What else do we know about quadratics? If you can dig back into your memory, we mentioned it. Anyone? We said that of all convex functions, it's the nicest, right? Because it's got just the right properties. And so there's the mathematical advantage to having Gaussians as well. And so here's what I'm going to say. I'm going to say that my encoder and decoder must be such that they reconstruct the input. But on top of that, I'm going to impose the constraint that the variable z that connects the encoder to the decoder is a Gaussian. How do I enforce this restriction on z? So we can do it in one of two ways. I can take large quantities of the data, and I can look at the distribution of all of the z's for all of the data. That's going to have some distribution. And then I can try to minimize the KL divergence between that distribution and the standard Gaussian. If I do that, then the distribution of z's is going to become Gaussian, right? But there's another way of doing it, which is the easier way, which is to say that if a variable is Gaussian, then an expectation, the log likelihood of data from that, of instances of that variable, computed using a Gaussian, is going to be higher than if you compute it using any other distribution. Because if you compute it using any other distribution, that's probably going to assign too low probabilities to data that are actually high probability, or too high probabilities to data that are actually low probability. Either way, you're going to get chewed, right? So this is the second one. You want to maximize the log likelihood of the z's as computed from a standard Gaussian, or alternately minimize the negative log likelihood. This is something that we use in machine learning, statistics all the time, right? So let's take a look at how this works. If, again, go back, and this is the formula for the Gaussian. If I take the log Gaussian, it's minus 0.5 d log of 2 pi. This is not a function of any variable. So all you're left with is, since I'm taking the negative log likelihood, plus 0.5 norm z squared. Beautiful. That's a quadratic, right? And so I can just say, OK, I'm going to try to minimize the norm z squared, which is basically the output of the encoder. The 0.5 is just a scaling factor. I can get rid of it, right? And so the overall loss that I would have is something of this kind. I want to minimize the error between what the decoder reconstructs and what it started off with, while also minimizing the squared norm of z. And this lambda is basically a balancing factor which determines how you balance these two components of the loss. Now, would this work? Do you guys think this would work? Anyone? Yeah.
I don't think so, really, because you're just trying to make z's as small as possible.
Exactly, right? What this is going to do is to keep pushing all the z's towards zero. And the limit, if you do a perfect job, all z's are zero, right? Or very close to zero. If I begin randomly sampling z's from a standard Gaussian, that's not really going to give me, most of the z's that I see are not something that I would have seen in the training data, because this is pushing all the z's towards zero. They're all going to become very small, right? So this mechanism is not going to work. What we really need is this first mechanism, minimize the KL divergence between the distribution of z and the standard Gaussian. And that's where it becomes kind of ugly mathematically. Now, it's not really bad. It's not hard math. It's not painful. It's just painful because it's tedious. But your good fortune is that I'm going to breeze through it in one lecture. and then you'll never see it again. Anyway, so here's your second problem. Too early in the morning.
Stay awake better in class though, so it's good.
Okay, guys, it's just 2 true-false questions. What are the answers? What's the answer to the first question? Anybody? Second one, Oliver?
I said false.
You'll be right? A regular autoencoder trained to also minimize the length of the hidden latent representation implicitly assumes that the Z's come from an isotropic Gaussian, and the output of this AE is still going to lie on a low-dimensional manifold because the manifold itself is decided by the dimensionality of Z and nothing to do with the distribution of Z itself, right? But this is not going to work, right? This does not adequately account for the variation in the data. It will push all training data to simply have a very small Z with very low variance. And that's not going to work. We have a bunch of examples. I'm not going to show them simply because, A, I don't have them on the slides, B, I'm out of time. Now, so let's go back and start all over again, right? Is everything I've said so far making sense to you?
Yes.
Right? Thank you. That's very nice of you. So the generative portion of the model, this is the decoder, right? This is the one that takes in a Z and generates data. Now, once again, my problem was to learn a distribution for, say, faces, and then somehow come up with a mechanism for drawing from this distribution. And the way we did this was to realize that the set of all faces lies on a low-dimensional manifold in the high-dimensional space. You can have 100 million pixels in your image, but if you consider all face images, they lie on a very thin, low-dimensional manifold in this 100 million dimensional space, right? So how do I characterize it, and how do I sample from it? And the mechanism we chose was to say that I'm going to start off with a Z which belongs to, say, a 100-dimensional space, if that's what I think the true degrees of freedom in faces are, right? And so then this, I'm going to put through some function, this is some network, which outputs X. And this network is going to take this 100-dimensional sheet and fold it so that the folded sheet now represents the manifold of faces. And then subsequently, anytime I draw a Z from here and pass it through this guy, it's going to pick a point from the manifold of faces. And the problem we are left with is, how do I choose which Z? I know that it's going to be on the right surface, but I still need to be on the correct location on that surface. And everything is about trying to figure out, how to pinpoint the Z's, right? So when I do this, using simply, when I just minimize the norm of Z, all you will find is that for Z equals 0, it produces a pretty good picture of an average face. But if you go off 0, it's going to produce nonsense because, it hasn't learned, right? Now, again, the decoder we know can only generate data on a low-dimensional manifold of the space, of the same dimensionality as the input. So it transforms the planar input space to a curved manifold in the output space. The moment you curve things, why Gaussian? I can use any odd distribution, right? But whatever the distribution is, if I have a sheet of this kind, right? This is my planar sheet, and I have a Gaussian on it, and then I begin folding and twisting and turning it. It's going to be a curved surface, but is the distribution still going to be Gaussian? What do you guys think? It's going to lie on the surface, right? Something that only lies on the surface and is twisted and turned can be anything. There's no restriction anymore. I can take a circle, and if I twist it and turn it and warp the line, it can look like an ellipse, it can look like 2 pinched blobs, it can look like any odd thing. And so if I learn the function properly, it's going to learn to manipulate this Gaussian so that what comes out on the outside looks like the distribution of faces on that surface. And so that's the idea. This is a mechanism called reparameterization, where you start off with a standard distribution, somehow modify the data so that you end up with a new distribution, okay? So here's the thing. I don't know what the distribution of the actual latent distribution is. What is the dimensionality of the manifold that faces lie on? I am going to take a guess. Odds are my guess is wrong. So even if I get the best 100-dimensional fit to this manifold, a lot of data will not lie on it because the data itself might be, say, 120-dimensional or 1,000-dimensional. It's still much lesser than the million dimensions of the image, but I have missed the manifold itself, right? And number one. And number two, even if I somehow magically manage to capture the exact dimensionality of the manifold, the faces are not going to lie exactly on the manifold. They're going to be a bit of a fuzz around it because, if you take a picture of a photograph of a person, there's a lot out there that's not all face, right? I mean, you're going to have small variations. And so our simple model doesn't capture any of this variation of the manifold, which could be because A, you got the dimensionality wrong, B, the data are just varied, right? So how do you capture it? We're going to assume I need to account for the off-manifold variation. I have the data. I've assumed that my faces are 100-dimensional, or they live in a 100-dimensional space, but in reality, they live in 180 dimensions, right? Somehow I must account for this error of the surface so that I can learn this 100-dimensional manifold properly. The way I will account for it is to say there is a noise, and this noise is something that I add to data points on the manifold to get real faces. That making sense to you guys? Right? And so this noise, since again I cannot make any assumptions, this noise I will assume is full dimensional. It doesn't have any low dimensionality to it. It's in the entire million dimensions or whatever the dimensionality of my pictures is. And so now if I train the model, there's something crazy that can happen. I can just somehow magically push all the information about faces into the noise. That's not a good thing, right? Then the model itself has learned nothing about faces. So I have to minimize this noise so that the model learns everything as much as it can about faces. Making sense to everybody? Right? And so you want to train the model to minimize this noise so that it has captured the principal manifold most effectively. This is the smallest amount of noise to be added such that the distribution at the output fully explains the distribution of the training data. Furthermore, you're going to assume that the noise that you're adding is Gaussian. Why would you assume that the noise is Gaussian? Anyone? We mentioned something about it briefly just a little while ago. If the noise were not Gaussian, it means the noise has structure. Correct? If the noise has structure, that's something the model can learn. The model should capture all the structure in your data. If it does a good job of capturing all the structure in your data, all that remains is unstructured Gaussian noise. So you're going to assume the noise is Gaussian. That making sense to everybody? Right? And so now, if I'm adding noise to the output of the model, I feed some Z into the decoder, some E comes out, I'm adding noise. The output is no longer deterministic because the noise is being drawn from some random distribution, right? And so, can you shut your laptop at the back, please? Rules of the class, laptops are shut, right? And so, this decoder is now what we will call a generative model for the data. It has a generative story for how the data are produced. There's a k-dimensional vector drawn from a standard k-dimensional Gaussian, is passed through the data, the model. The result lies on a k-dimensional space. Then a full rank low amplitude noise is added to it to generate the final data. The actual distribution is a fuzzy region around this manifold. Now we want to train the model. If I knew, how do I train the model? Now this becomes a standard regression problem. In any regression problem, you're going to assume that there's some residual noise and it's Gaussian, right? And the reason you assume it's Gaussian is that's when most of the structure is pushed into the model. So we know how to train regression models. For regression models, I know the input that goes in, I know the output, X, and I train the model to minimize the error that you get when the input Z is pushed through the model to compute an output. That's your standard regression model, right? I could do that over here, except I don't know the value of Z for any input. For every input, if I knew the value of Z, I could take the XZ pairs, the collection, push them through a standard regression training, and I just learn my model. What can I do if I don't know Z? Anybody? I don't know Z, right? What can I do? Again, this is a regression model, if it's making sense to you guys, right? My regression model has something of this kind. Your standard regression, you'd be given, your training data would be X comma Z. Then you put your Z through some model. It's going to give you some X hat. You have the true X. You minimize the error. This is how you train your regression, right? This would be easy. Z is the latent variable, it's a position on the manifold. If I had the Z for every X, I could train this network, right? I don't have Z. What can I do?
Estimate it.
I can guess it, right? And so we don't have Z, so we're going to guess the Z. And that Z, the guess for the Z is what comes from the encoder. Making sense to everybody? So now, if I look at it this way, I have to guess the Z, right? And now, how do I guess the Z? From the X, if I have a current encoder, I can push the decoder, I can push the X back through the decoder to get the Z. And now I have a guess for the Z, right? This is a standard approach. I'm going to have a current guess for the model. Then for every X, I can push the data back, reverse through the model to get the guess for the Zs. I'm going to have a collection of X's and Z's now. I can go back and re-estimate my regression. I can keep repeating this process. And eventually, when the thing stops changing, I know I've learned a proper regression. That's basically what we want to do over here. And except pushing the model data back through this guy is hard because the noise that we added comes from a Gaussian distribution. There isn't a unique noise that could have produced the X. All of these X hats could have given you this X, right? So there isn't a single Z that could have generated any given X. What we need to characterize is the collection of Zs that could all have resulted in this X. And so there's an entire distribution of Zs that could produce a given X. And the distribution has a probability P of Z given X. So we need to characterize this somehow. And so the encoder's job is not going to be that of finding a specific Z for any X. It's going to be characterizing the entire distribution of Zs for that X. And the way you're going to train the model, in principle, is this. This is your decoder. If you knew the Z for every X, then you could put the Z through the decoder. You have the X. You minimize the error. This is your standard regression, right? Now you don't know the Zs. So what we will do instead is that you're going to put the X through the encoder. And it's going to give you a collection of Zs, a distribution of Zs. And then you're going to put this through the decoder, and it's going to give you X hat. Except you're going to put every one of these Zs through the decoder, because they're all possibilities, right? Each of them is going to give you some guess X hat. And then you're going to minimize the error over the set or the entire distribution of Zs that could have generated this X. That making sense to everybody? Right. For that, we need to be able to do one of two things. Either you want to be able to mathematically characterize how pushing the entire distribution through the decoder works, or you're going to have to, you won't use all of them, you're going to pick one of them. You're going to sample it somehow. And you're going to pass the sample through the decoder. Is that making sense to you guys? Guys on Zoom, that making sense? Somebody say yes on Zoom. Otherwise, I'm going to assume there's no one on Zoom. Okay, they're saying yes, okay?
Professor, I have a question.
Yeah. What is it?
Can we like make it so if there's multiple classes within our data, we can select the class when we're doing generation? Or is this like only for a certain type of data? There's no way to like select
We can
certain
make it
class.
class specific. We can definitely make it class specific. And the way you would do it, so in the, can you postpone this to the end of the class? Because I want to finish this lecture, and then I'll
Yeah,
answer that
sure.
question. It's a very nice question, okay? So this is the variational autoencoder, because again, minimizing the error over all possible z's is challenging. So we're going to find a lower bound, a variational lower bound, and that's for the error. And that's what we're going to, actually it's a variational upper bound to the error, and that's what we minimize, or a variational lower bound to the likelihood, which is what we maximize. And so here's what we have. The encoder computes the distribution of z's for any x. The decoder tries to convert the expected output of all the z's to the target x, or more typically it picks a random one sample from these z's. And so the overall training procedure is the encoder has its own parameters, theta. We have to estimate the theta so that the z's the encoder produces are going to become something like the face we want, right? Then for the decoder, those z's must be put through the when they go through the decoder, they must become faces. So there are two sides to it. We have to learn this guy so that it produces the right z's, and we have to learn this guy so that those z's become the face. Makes sense, everybody, right? And then we have the constraint on the z, because again, we can't just let the z be any odd thing. We want the z to be standard Gaussian. So we are saying that now, for any given x, not all z's are going to give you that face. The set of z's that could give you that face is going to be very restricted, some small region in the overall distribution of z's, right? That's what the encoder is doing. It's trying to characterize this distribution. But the overall distribution of z's is a standard Gaussian, right? And so what does that mean? It means that if you look at the conditional distribution of z's over all possible faces, cumulatively, they've got to look like a standard Gaussian. Does that make sense? Right? So, which means that if I integrate P of z given x over all possible x's, where some x's are more probable than others, this has to be a standard Gaussian. But again, that's just integral of P of x, P of z given x, dx, right? Which is going to be integral of P of x comma z dx, which we know is just P of z. We're saying this guy is standard Gaussian, right? That's what this means. Okay, so we are going to try to minimize the error between this guy and the standard Gaussian. But we still have a problem. And the problem is, what the hell is P of z given x? Now, if I take a sheet and I fold it in some crazy way, and I make it some crazy manifold, right? And so I have this crazy folded sheet, and I'm saying that, and I've twisted and turned it in the process of modifying it. And I'm saying on the twisted and turned region, this portion of the space is going to become this face. When I go back into the input before twisting and turning, can I actually identify the corresponding region in the planar version of z that could have given the face? That's going to be very hard, right? Because the whole thing was twisted and turned, and we have no idea how untwisting it will work. So that decoder is a complicated function. I don't know what this guy looks like. It's definitely not going to look like a Gaussian. It's going to look some crazy, of all possible z's, right? Maybe this little portion or maybe this little portion is what became a particular face. But I have no way of determining this, right? So so the encoder has to characterize this, but this can be arbitrarily ugly. The encoder cannot actually characterize it. And so we're going to do something. We're going to approximate it. The way we will approximate it is, I know what kinds of distributions I can characterize. And so I'm going to come up with some distribution which captures most of this, but is as compact as possible. around the set of possible z's that could have generated a given phase. Again, that making sense, right? And so this means, how do I actually get a Q, an approximation, which is as close as possible to the P of z given x? I want to minimize the divergence between my approximation and the true guy, and I want to do this such that this holds for most x's. So I want to do this, minimize this expectation of this divergence over all possible x's, right? Make sense? Right. So this is what we're going to do. Now, this is where the ugly math comes in. The ugly math is as follows. If I look at the, guys, if you have any doubts about this so far, let me know. Any questions? Yes, no? No, okay. You're supposed to have questions. This is some complicated stuff. In my very first class at CMU, I had this big kid who called himself Alpha, who came into my office after class. He sat himself down and he said, I have no questions because I didn't understand a single word. Right? That's a perfectly valid thing to do. I will spend time and correct things for you. So what is the KL divergence between two distributions? It's the expected logarithm of the ratio of likelihoods assigned to the data by the two distributions, right? So it's going to be the expectation over all z's drawn from Q, which is the approximation that you have, meaning the expectation over all z's from this guy. You always want to take the larger one, because if you take the smaller one, everything that falls outside the smaller one is going to have like negative infinity probabilities, log probabilities. You don't want that. You always want to start with the larger one. And so the expectation over all z's from Q of the log of Q over P. And of course, there's the expectation over all z's from Q of the log of Q minus the expectation of the log of P. We couldn't characterize this guy in the first place, so why are we back to this one? Well, we're going to use some Bayes rule. P of z given x is P of x, P of z times P of x given z divided by P of x. That's just Bayes rule, right? And so when I do this, I'm going to end up with expectation over all z's from Q of log of Q minus log of P minus log of P of x given z plus log of, so P of x, right? Is this making sense to you guys over here? Now, if you take the first two terms, the first two terms look like just the second line in the slide. So the first two terms just give me the KL divergence between Q of z for given x and the P of z, which is the universal standard Gaussian, right? The second term over here is simply expectation over z of the log of P of x given z. It's the negative log likelihood of x for a given z, which is x given, this is going to look like the distribution of the noise. And the third term, this is just P of x. P of x is not a function of any of the network parameters. It's something that we don't really need to worry about. And so the whole thing is simply going to say, I'm going to find the decoder parameters such that the KL divergence between the approximation Q and the standard Gaussian minus the negative log likelihood of the data itself is minimized. Now, this is about as complicated as the math gets. This making sense to everybody, right? Nothing fancy, right? And so, when I say that I want to make sure that the average of the posterior probabilities of z given x over all x's looks like a standard Gaussian, instead of just having the true posterior probability, I'm going to use the approximated posterior probability, which is Q. And so now, what exactly is this guy? The average posterior probability between the average KL divergence between the approximated posterior probability and the standard Gaussian. That I can just take this as, this is the expectation over x. That's what the math tells us. We as engineers know that an expectation can always be computed as an average over samples, right? So it's the average over all training data of the KL divergence between the approximated posterior probability X and the standard Gaussian. That's the math, right? And this is what we're going to try to minimize. But we're still left with what is Q, right? I just said I'm going to approximate my posterior P of Z given X, which I cannot characterize because maybe it looks something like this with a Q, which is maybe bigger than this guy, but something I can characterize, then I can compact it so that it matches it as closely as possible, right? That's where we began. Now Q is, again, recall that Q must approximate P of Z given X as closely as possible. Now we know the decoder is highly nonlinear. It's difficult to characterize the distribution of Z that could produce a given X. Now also we know that any given X is going to have to could have come from a region on the surface, the manifold that's produced by the decoder, right? And yet, if I actually knew the location on the manifold that any given Z became, then because I can add any odd noise, there's a distribution of faces that I could have generated from this location depending on the noise. And this distribution is simply going to be the distribution of the noise itself, centered to the location on the manifold, right? And in any case, the point is we cannot go back and find out what P of Z given X is. Again, it's a very complicated slide stating the obvious, that if I have some region on the surface, on the curved surface, there's no way for me to go back and say over here, it's this nice clean portion of the original latent space, right? So we're going to go back and, so we're going to look at some mathematical realities to deal with this. First, what's the property of a standard Gaussian? We said Z is a standard Gaussian. It's an isotropic Gaussian, right? Which means that regardless of which direction you look at this distribution from, it's going to look like a standard Gaussian. Secondly, if I slice the standard Gaussian along any plane, at any plane, this is a property of the standard Gaussian. It's unstructured noise. It doesn't matter how you look at it, it's going to be unstructured. You're not adding structure. If I cut it along a line is not providing any information. The distribution on that line is going to be maximally unstructured. It's going to be standard Gaussian. If I slice it along a plane, it's going to be standard Gaussian. That is the property of the most unstructured noise you can think of, right? So, is that making sense to you guys, right? And so this property that is going to hold regardless of the line or hyperplane which you consider. So if I say I'm going to look at the distribution of this variable where x plus y is 3, or x1 plus x2 is 3. Along that plane, the distribution is going to be standard Gaussian. I can say, I can draw any odd slice, and the distribution is going to be standard Gaussian because it's maximally unstructured. That's why we wanted the unstructured Gaussian, because it's A, it's making no assumptions about the data. B, by making no assumptions, it gives you this very nice property, right? Now this has a secondary consequence. Instead of looking at a plane, if I look at something that's almost a plane, a mildly curved surface, and if I look at the distribution along the mildly curved surface, if the surface is not curved too much, if it's not varying too much from a plane, on the mildly curved surface, the distribution is going to be approximately Gaussian, almost Gaussian. That making sense to you guys, right? And so the only difference is that if I choose a plane, this Gaussian is going to be zero mean unit variance. If I choose a mildly curved surface, the distribution on that is going to be almost Gaussian, but the mean won't be 0 and the variance won't be 1. Right? That making sense? Right. So for nearly linear functions, so what is a curved surface? A curved surface is basically a surface of the kind f of z equals 0 or f of z equals constant, right? So where for nearly linear functions, the distribution on the curve represented by this function is going to be almost Gaussian, but the mean and the variance of this Gaussian are going to depend on the function and where on the function you're reading it. that making sense to everybody? And where's my yes?
Yes.
Okay, thank you, right? So we're going to use that. And here's your third pole. Guys, if any of this is getting to be a bit too dense, just let me know. I can spend some time after class and go back and try to unravel the really tangled bits. I'm trying to make it easy, but okay, it's only two true-false questions. What's the answer to the first question? True. How many of you think it's true? Okay, can everybody say true? Thank you, right? What about the second one? Just, I'm not going to prompt you. Everybody speak out the answer that you think is correct together, and we'll see what the chorus sounds like. If it sounds like noise, I've messed up, right? 1, 2, 3. Okay, great. We've done a good job, right? The Z is a random vector with an isotropic distribution. The conditional distribution of the projection on any affine plane is also going to be isotropic Gaussian. If Z is a random vector with an isotropic distribution, the conditional distribution on any curved surface of low curvature is also going to be approximately Gaussian, right? And this means that I can actually assume that this guy over here, if I can assume that my encoder is not folding the surface too much in any given location, if the curvature is low over the entire space, then I can approximate this guy to be a Gaussian, right? I can say Q is Gaussian. If Q is Gaussian, how do I characterize a Gaussian? What are the properties of a Gaussian? Anyone?
Mean and variance.
Mean and variance, right? Now I have a mathematical formalism. All that needs to do is this guy, the encoder, just has to, for any given x, it only has to compute the mean and the variance of this Gaussian. Is that making sense? Right? Now, once you do this, we're approximating P of z given x as a Gaussian with a mean that's a function of x and a variance that's a function of x. And of course, it's going to be mu of x semicolon phi. Phi is represents the parameters of the network that computes the mean and the variance. Now, the variance itself, there's no restriction on the variance, but I'm going to assume that the variance is a diagonal variance because mathematically it's the most tractable one. And now I'm going to use Q as a proxy of P, right? So we figured out what the Q looks like, the approximation. Now next, we have to estimate the parameters of the encoder such that it computes a Q so that when I sample from this Q and pass it through the decoder, the output looks like my training data, like the face that I wanted to reconstruct. Making sense, right? So we're going to do this, and the constraint, of course, is that the average Q of z given x has got to be as close to Gaussian as possible. How does that work? Here's my Q. Here's my z. Z is coming from a standard Gaussian. Z is coming from my Q, not the standard Gaussian, right? If Q is a good approximation, then all z's that I draw from this Q, when passed through the decoder, must generate an x that looks like my training data, like my face. Okay? So furthermore, I'm going to assume that this noise, I can make any odd assumption about the noise itself over here. And this is math. Well, one of the most simplifying assumptions is that the noise that I have, that I must add to the output is also isotropic. The reason, once again, isotropic Gaussian means it's unstructured. If that's unstructured, it means that the model has captured most of the structure and the data. So we keep falling back on this. We like using isotropic Gaussians because if the model actually generates errors that are isotropic Gaussian, it means the model has captured the structure and the data, right? So the probability of x given, distribution of x given z, you're just adding the noise e to x hat. If E is a Gaussian, this is just a standard Gaussian. This is just a Gaussian whose mean is at x hat. And the variance is sigma squared I, right? So I can write down the formula for this, which is the log probability of x, this guy, given that if I sample Z from Q, the output of the decoder is going to be x hat. If I give you this x hat for that particular sample, what is the probability that I will see this face? That's going to, or what is the log probability? That's just given by the log of the Gaussian, computed with the mean at x hat. And so I want to find out the encoder parameters. Again, my job is to learn the encoder. The encoder must compute as Q such that samples from Q give me, when transformed, look like my face. So I'm not optimizing my decoder over here. This is about optimizing my encoder. I'm trying to find out how do I optimize my encoder such that the approximation Q gives me samples that look like that get transformed to my face, right? And so I'm going to be maximizing the log likelihood of my data given Z's from this Q. And this I can do using backpropagation, right? I can, instead of the log likelihood, I can have the negative log likelihood, which looks like the formula over here. I can minimize the negative log likelihood. This looks more like a standard loss. And then subsequently, you want to minimize this loss with respect to the encoder parameters so that it learns to compute the Q properly. That makes sense to everybody. I know there are a lot of tangled threads over here, but it's really not that tangled. I'm trying to learn the encoder so that when I sample from the distribution computed by the encoder, and I pass those samples through the decoder, it looks like a face. So the way I will do it, I'm going to draw these samples, pass it through the decoder, compare it to my face. I have an objective, which is the error between what the decoder produces and the real face. I'm going to backpropagate it to fix my encoder. The specific loss that I chose over here is the negative log likelihood. You could choose something else. That principle makes sense to everybody? Right, okay. And so now over here, we are sampling a Z from Q. When I sample from a distribution and then pass it through the decoder, sampling is a non-differentiable process. How do I backpropagate through a non-differentiable process? So this is where the other reparameterization method that people like to harp about in VAEs comes in. When I want to sample from a non-standard Gaussian, if I have a Gaussian somewhere, right, how do I sample from this? The way I would do this is I sample from a standard Gaussian, then I scale this sample such that the variance becomes like so by multiplying it by the inverse standard deviation, right? Or multiplying it by the standard deviation, right? Which is the square root of the variance. And then add the mean so that the whole thing goes out here. So I can sample from a standard Gaussian. And like, where is this? This epsilon. I multiplied by the inverse of the square root of the variance and then add the mean. And that's going to give me a sample from the target distribution that I want. But when I write it in this manner, my mu and epsilon become part of my sample, and now this can be differentiated. I can actually differentiate it with respect to, I can differentiate the Z with respect to the parameters of the encoder, theta, right? So that's a sampling process that's differentiated. And now, so I can actually compute the derivative of the loss that I got over here with respect to the parameters of the encoder by computing the derivative with respect to Z, and then multiplying that by the derivative of Z with respect to the encoder parameters, right? So chain rule. Again, I don't expect you to get everything, grasp everything as I present it in class. There's a lot of stuff, but if you're paying attention, the general idea must come across enough that when you go back and look at the slides, it makes sense, right? Do you think you're there? Yes, no?
Yes.
Okay, you guys are very quiet. Okay, let me try again. Yes or no?
Yes.
And this is not working. Okay, my next question I really need a very loud yes. Keep in mind that I'm jet lagged. I've just come back after 3 months of 3 very horrendous months. I've traveled 68 hours to be here. I'm more tired than you. So you must wake me up with your yes. Okay? The second is, how do I train the decoder? How do I estimate the phi? So let's say I've learned the encoder properly. The encoder is doing a very good job of approximating the posterior probability of z given x. So anytime I sample from it, the decoder must give me a good phase, right? So how do I estimate the decoder? The way I do it, this is like a standard regression, right? I pass the z through the decoder, it's going to generate an output, and I'm going to optimize my decoder so that the noise that I must add to account for the error is as small as possible, right? Simple enough. Or alternately, I'm going to do this by saying that if I assume some kind of a distribution for the noise, I want the variance of that distribution to be as small as possible. That's how I want the mean of the noise to be 0 and the variance to be as small as possible, right? That's how I make sure that the noise is really small. So alternately, this means that when I compute the probability of the noise on a distribution, right? The distribution, the probability must be as high as possible, because when the probability is high, the variance is small, right? We're assuming that it's a Gaussian distribution. And for a Gaussian distribution, you know this. The Gaussian distribution has this shape. If the probabilities are low, the variance is large. If the probabilities are high, the variance is small, because the volume has to be 1. So you're going to be learning the model parameters to make the probability of the noise as high as possible while having a mean of 0. That means that the spread of the noise is as small as possible. That makes sense to everybody? And so this is just maximizing the log probability or minimizing the negative log probability of the noise. And again, we know the distribution of the noise. If I give you the z, I give you the x hat. If I give you the x hat, then the probability distribution of x is just a Gaussian, which is just the distribution of the noise itself with the mean shifted to x hat. So I can, which is this term here, I can compute the probability of x on this distribution. This is the negative log likelihood. I want to minimize it. Alternately, I'm maximizing the probability. That sounds very mathy, but the basic idea is just that. I want to make the probability of the noise as high as possible, which is the error between what the model computes and the true data. I want it to have 0 mean, and I want the probability to be high. That way I know that the spread of the noise is as small as possible, right? And so this NLL must now be optimized with respect to the decoder parameters. So here, of course, we have the final constraint on z, right? You want the average Q of z to be as close to the standard Gaussian as possible, which means that I want the KL divergence between Q and the standard Gaussian to be minimized. There's a formula for it. I've written this on the slide. I'm not going to read it out. I don't expect you guys to understand it or believe it. But then these days, there's a magical tool, Claude.ai, Gemini, right, .google.com. So you can actually ask it for the KL divergence between two Gaussians, and it's going to give you this formula. And as we all know, these days you don't need to derive anything, you just believe Google, right? So that's what I did. Okay. Now this is a function of the encoder parameters. And so you have this whole loss, which is actually, it ends up looking very much like a quadratic. So all the terms that you end up with, I've given you the logic behind every term. I haven't actually derived the math. In my experience, anytime I do math on the board, which I can, nobody follows me, right? What also happens is that when I start at the top left corner of the board and I get to the bottom right, I have no idea what I've been writing. I've lost myself. So it's best that I just put it on the slides. I expect you guys to go back and take a look. But the idea that I used in deriving these formulas should be clear, right? And the one extra thing is that this guy, the error between the output of the decoder and the true data, that's a quadratic, right? This one, the squared norm of the mean, that's a quadratic also. There's the log of the variance, that's not a, and the trace is a quadratic as it turns out. The log of the variance is not, but it's differentiable. And so you end up with this nice loss function which captures everything that we need. First, the encoder must be such that samples drawn from the output of the encoder when processed by the decoder look like your data. The decoder must be such that when these samples are passed through the decoder, they look like your data. And then the posterior probability must be such that on average it looks like a standard Gaussian. These are the three principles that we had, right? All three are captured by this one simple loss. And so here is the overall model. That makes sense to everybody?
Yes.
Yes.
Okay, thank you. Right? I don't expect the maths to make a lot of sense because there's no way I'm going to convey that much math in 70 minutes and have it make sense. But the general principle makes sense, right? And so here is what you have. This is the encoder. X goes in, it learns a Gaussian. The Gaussian is approximating the posterior probability of z given x, right? Then you're going to sample a z from this distribution. Like I said, there are many z's that could have produced the x. You're picking one at random, right? And then this sample is put through the decoder, which tries to generate a phase. And now we have a loss which quantifies the error with all the constraints. It quantifies the error that this guy makes in converting the z to the x. It quantifies the error that this guy makes in approximating the distribution of z, such that those z's become the x. It also quantifies the constraint on this z that the z must be a standard Gaussian. All of these three in one simple compact loss. That making sense? Right? Okay. And that's what we minimize. Where are the neural networks? This guy, of course, is a neural net, and this is a neural net with two outputs, the mean and the variance. Easy, right? And so this is what it looks like. This encoder is a neural net which produces a mean and a variance. It has a common set of parameters. And the decoder is also a neural network, right? And now once you train it, what was the point of this whole process, all of this exercise? The point of this exercise was, in case you have forgotten, we wanted to come up with a model that you could sample that learns to characterize the distribution of the data that you're interested in, of the particular class, like faces, and so that you could sample from it, right? And the point was, and the way we did it was that we chose the dimensionality of the manifold that we thought the data lay on, and we defined our latent variable, z, as a standard Gaussian on this manifold. We wanted to put this constraint on z because if you didn't, then you'd have no control over what values z would take. And then we learned this model such that this one would transform this standard Gaussian in the z space, twist it and turn the space so that it actually became a distribution on the target manifold in the output space. And thereafter, you could sample any z from the standard Gaussian, pass it through the decoder, and the output would look like something from your target class, say a face, right? And so this was your decoder, right? And the reason we needed the encoder was that in order to learn the decoder, you needed to know the z for every x. And you needed to constrain some of the z. But once the model has been trained, you can throw the entire encoder contraction out, and just the decoder with the z's is going to give you a generative model. Okay? So this is the VAE. It's an autoencoder with statistical constraints on the hidden representation. The encoder is a statistical model that computes the parameters of a Gaussian that approximates the posterior probability of z for any given x. The decoder converts samples from this, and we model it as a Gaussian because that's most convenient. You could model it as anything else. You just have to adapt the math for it. The principles still hold, right? And then the decoder converts samples from the Gaussian back to the input. And the decoder is a generative model that, when excited by samples from a standard Gaussian, gives you data from the class that you're interested in. Okay? So this is the variational autoencoder. Again, the decoder is the actual generative model. The encoder is primarily needed for training. The encoder can also be used for other purposes, right? So what exactly would that be? Is there an eraser here, duster? So if you learn your model properly, you expect some properties of continuity. What do I mean by that? In my Z space, I have a standard Gaussian, which has an isotropic distribution. This Z has been modified by my decoder, and now I have this crazy surface, right? And this standard Gaussian now has maybe become something like this over here, and may even have split into different regions, because the decoder can do any odd thing, right? And anytime you sample from this Z and pass it through the decoder, it's going to pick samples from here or here or here, which will give you a real face, right? Now, if I choose any point over here and any other point over here within the Z, and I traverse a line between the two, the intermediate points must represent some notion of continuity in the latent space, right? Now, what are these two guys? What this means is that suppose I have one x, x1 and x2, and I put each of these through the encoder. x1 has a mean, which is maybe here, right? x2 has a mean, which is maybe here. If I choose a point somewhere on the line, if I've learned the model properly and all the expected continuity is held, then then this point, when passed through the decoder, must give you something that looks halfway between x1 and x2, right? So we can also use this for those purposes, right? Yeah. That's what you're here for. Track zoom. Tracking zoom.
Progress.
Yeah. All right, guys. First question. What's the answer?
True.
True. And the second question, what are the true statements? Anybody? Yes.
All.
All? Let's see. Guys on Zoom, do you have an answer? Anyone on Zoom? All. Okay, let's see. Right, the variational autoencoder is a generative extension of autoencoders that models probability distributions. The standard VAE assumes a latent representation that has an isotropic Gaussian. It requires addition of Gaussian noise to the output of a regularized VAE in order to permit the output to fill the space beyond a lower dimensional manifold. The decoder can be used to generate samples from the distribution it's trained on if the input is drawn from a standard Gaussian. That was the idea, okay? So when the paper first came out, here are some examples from the paper. The top one, that's a VAE trained on MNIST. And then afterwards, when they sample X, sample Z and pass it through the decoder, you can see that what comes out actually looks like digits. Like it's not digit-like, they're actual digits. It's done a very good job of learning the distribution. The lower one, they trained it on faces, and it kind of looks like faces. Does it look like faces? Right. What's wrong with this, though? Something crazy about those faces, something off? Or are they all just fine as faces?
It's not that clear.
It's not that clear, right? Let me get back to that point. That's something, okay. So again, remember this thing I mentioned where if you traverse 2 points, traverse a line between 2 points, you should get some kind of a continuity of variation. So here's an example where the thing was, these 2 guys were passed through the encoder. And then if you pick intermediate points on the line that connects the 2 means and pass them through the decoder, it actually no, here this and this. where the two endpoints, the one in the middle actually gives you a smiling face, right? Or this and this. The one in the middle gives you a partially frowning face. It actually captures the continuity of the manifold. It's quite impressive, right? It does a very good job. This is the foundation of much of what we do with diffusion models and such like today. So it's something that you really need to understand, okay? So it's a simple statistical extension of the autoencoder. It's an excellent generative model for the distribution of data P of X. And someone asked me about, are these specific to a class? I have a little time, I'll get back to that, right? But here are the limitations. We needed an approximation, Q, because there was no way of characterizing what the reverse was. If you pass the data back through the encoder or through the decoder, what was the value of Z that gave me this particular X? There was no way of actually characterizing this. But what if I actually put restrictions on my decoder, on my model, so that for any given X, I could go back and find the Z? The answer is that if you can do that, you end up with a model called a normalizing flow model. So the normalizing flow is basically just a variational autoencoder where the decoder is invertible so that you can find the Z. Now, for this to be invertible, right, what does it say about the dimensionality of Z versus the dimensionality of X? Anyone? They have to be the same, which means you're not making any low dimensional manifold assumptions on Z, right? Nonetheless, the model actually learns the restrictions on Z if you train it properly. So it's pretty powerful. The other thing is this guy, right? In the pictures that we saw, these guys were not, they're supposed to be faces, but they're not really looking like faces, right? I mean, they're fuzzy faces. What does it mean? Now, in our encoder, in our model, we had this assumption that when you train the model, Z goes in, then the decoder, which is actually a generative model, produces an X. And then to get the actual X hat, to get the actual X, you had to add an uncorrelated isotropic Gaussian noise, correct? Noise. That means the noise that you add to X hat doesn't look anything like faces. That's the model, right? If that were true, then these should have been noisy faces with speckled Gaussian-like noise, right? But if I were to take an underlying face for each of these guys and look at the difference, do you think the difference would be face-like or is it going to be noise-like? What would it look like? This looks like a fuzzy face, right? What's the difference between a fuzzy face and a clear face? Is it going to be noise or is it going to have face-like structures? Noise? Not necessarily, not really, right? You get all the outlines are gone, the structures are gone. All of those are very face-like, correct? So the reason this thing looks kind of blurry is that if you look at the difference between this eye and a real eye, that's where some of what makes an eye is captured, right? So the noise is not really uncorrelated. It's not independent. No matter how well you train the model, it hasn't actually managed to become independent. The reason for that is that traversing the gap from Z all the way to the distribution of X, a standard Gaussian to a distribution of X, that's a huge gap. The model is not able to do this properly. The model would do it better if the Z were closer to the distribution of faces in the first place, right? Where could such a distribution be obtained from? A distribution that is closer to the distribution of faces. Anyone? How about this guy? This guy is actually giving you something that's not quite the distribution of faces, but it's like faces, right? So which means that I can actually have a VAE out here, and the output of that guy is going to be closer to the distribution of faces, right? But then that's going to have the same problem. So I can keep nesting things. And so when I nest VAEs one inside another and place some restrictions on the nesting, you end up with what's called a diffusion model. And nested VAEs with a restriction on linearity, you end up with a diffusion model. We'll cover these in the next class. Sorry for going over. Thank you. Thank you, guys. And it's good to finally see all of you in person.
Yeah.